Hi, my name is Tessa Hansknecht, and I am the project manager for Project 19408, Grocery Mobility Devices.
I'm Raymond Lowry. I'm the mechanical engineer on the project.
My name is Colin Idell. I'm the electrical engineer on the project.
My name is Ellis Cleveland. I'm the industrial engineer on the project.
I'm Brian Antidiatro. I'm the biomedical engineer on the project.
Our team was tasked to redesign a current personal mobility device, PMD, with enhanced accessibility within grocery store environments. Users report only 30% accessibility to grocery store environments with current market personal mobility devices. While some items are reached easily while seated, items higher or lower than the user's sitting reach require leaning to acquire. Our client wanted us to modify an existing PMD to increase the vertical reach of the user and improve reachability to bottom shelf items while maintaining the weight capacity of the PMD for both the user and groceries. Additional customer requirements included comfort, intuitive controls, and improving the PMD's interaction with bystanders, all of which were addressed by our design but held at a lower priority than the reachability requirements.
Our design is composed of three main systems: a seat lift, a basket assembly, and auxiliary systems located in the head module. These auxiliary systems include minor changes to the functionality of the device, such as improved battery gauge, a lead laser, and improved horn system.
The main feature of our device is our seat lift, being one of our critical CRs. This will allow users to extend their reach by at least 1 foot. In the future, the lift will be electrified. However, as a proof of concept, it is currently operated mechanically.
With the addition of the new lift feature, a new battery compartment was needed with a reduced height in order to maintain ergonomic seating conditions. The new battery compartment also needed to have a wider base for proper support beneath the lift. To maintain structural integrity, our design utilized the same attachment points to the PMD frame and conducted a stress analysis on our new design.
The basket has been redesigned to allow for more accessibility for the shopper as well as storage of compartment space. The basket basement has been removed and has been replaced with a movable platform. This ensures that when items are placed inside the basket, the basement slides down, and that way more space is able to be stacked on top of. 2 separate storage compartment spaces have been retained for personal items, and the bottom of the basket has been removed and extended to allow for this movable basket bottom.
To meet the goals of our problem statement, our design features additional components that work in tandem with, or sometimes even replace, existing electrical systems. The components added to the original PMD were an indicating lead laser, a new noise maker, a new horn button, a tip sensor, a tip indicator LED, and a new battery gauge. Some of these components were intended to be direct upgrades to existing hardware, while others were introductions to improve various aspects of the user experience. As you might expect, it was crucial to understand the original device's wiring before adding new components. Most of the time went into understanding what the original manufacturer calls the throttle circuit board that lives inside of the head module of the device. As you can see here, after many hours of debugging, it was found out which wires could not be touched and which ones could be repurposed. Our final design uses the same motor controller as the original device for central drive controls based on user input, with the addition of a microcontroller that serves as a middleman to handle our components. The microcontroller we chose to use was the Adafruit Metro, which is a functional copy of the well-known Arduino Uno. A program was developed using the Arduino IDE to handle the powering and control of our additional components, which was debugged over the course of many weeks. Once implemented, an entire new stage of debugging was required to make sure that wire traces were making it to their intended destinations. The figure on the left shows the final wiring diagram for our middleman microcontroller, the Adafruit Metro. Crucial information about the original device's power and control was provided via this silver RJ45 cable on the left. For this reason, final design uses multiple RJ45 breakout boards and other RJ45 cables to transmit data and power. To that end, this wiring diagram shows the final wiring for our proto board that interfaces all of the controls and power from each RJ45 cable.
Once we had our design, there are 3 formal verification methods we could choose from for each of our requirements: test, analysis, and inspection. For our project, we primarily conducted verification through testing. although there were some exceptions.
The same method was used to maintain aesthetics of the original device as to not dissuade mobility device usage. The target was fewer than 5 overall visual changes to the device, which the final device complies with.
We are very proud of the project that we've made, but if we were to have extra time, some features that we would add are a towing hitch so that a second cart could be trailed behind for more storage.
The motorization of the lifting mechanism.
Quick swappable battery should also be implemented to ensure the user never gets left without power.
For increased maneuverability, you could replace the singular drive wheel with multiple mecanum wheels to allow for omnidirectional movement.
And a help button can be installed so that access can always be made with the front desk.